Welcome to this masterclass on projectile motion. We will explore the physics of objects thrown into space, moving under the influence of gravity. A projectile is any object moving through the air after an initial push. We treat horizontal movement as uniform velocity and vertical movement as uniform acceleration due to gravity. To derive our equations, we assume an ideal model. We neglect air resistance and friction and assume the acceleration due to gravity, g, is constant. Our motion graph uses a Cartesian system, x for distance or range, and y for height. Launch velocity is a vector u at an angle theta to the ground. We break the launch speed into two components using trigonometry. The horizontal speed, u-x, is u cosine theta. The vertical speed, uy, is u sine a theta. In the horizontal direction, acceleration is 0, so the speed never changes. The distance covered in the x direction is horizontal velocity multiplied by time, t. Vertically, gravity pulls the object down with acceleration minus g. We use the displacement formula, where height y equals the vertical launch speed times time minus 1/2 gt squared. To find the path equation, we must eliminate time t. We rearrange the horizontal formula to solve for time. T equals distance x divided by u times the cosine of theta. We plug this expression for time into the height equation. This connects the vertical position directly to the horizontal distance covered. After algebraic simplification, we reach our final trajectory formula. This equation is in the form of y equals a-x minus b-x squared, which mathematically defines a parabola. The time of flight is how long the object stays in the air. Since the projectile starts and ends at ground level, the total vertical change, y, is 0 at the end of the trip. By setting height to 0 and factoring out t, we solve the part inside the parenthesis for the total flight duration. The final result is total time t equals 2 times u sine theta, all divided by g. This is exactly twice the time taken to reach the maximum height. To calculate the maximum height h, remember that at the very top of the arc, the object stops moving upward for a split second, meaning the vertical velocity is 0. We use the third kinematic equation for the vertical axis. We set final speed to 0 and solve for the displacement h. The result is h equals u squared sine squared theta divided by 2 grams. Notice that height increases with the square of the launch speed. The horizontal range, r, is the total distance traveled sideways. We find the range by multiplying the constant horizontal speed ux by the total time of flight t. By plugging in the values for ux and t, we get a formula involving both sine and cosine. We combine the u terms to get u squared. Using a double angle identity, we find the final formula. Range r equals u squared sine of 2 theta divided by g. To get the farthest distance, the sine term must be at its maximum value of 1. This means the best angle to throw an object for maximum distance is exactly 45 degrees. We can track the vertical velocity at any time. The vertical speed vy is the initial vertical speed minus gravity times time. The horizontal speed vx is the easiest to calculate because it never changes. It remains u times the cosine of theta throughout the flight. To find the true speed of the projectile at any moment, we combine our horizontal and vertical speeds using the Pythagorean theorem. We can find the direction of motion, angle beta, by calculating the inverse tangent of the vertical velocity divided by the horizontal velocity. At the maximum height, the upward speed is 0, but the object is still moving sideways. Therefore, the speed at the peak is simply the horizontal launch speed, u cosine theta. Projectile motion is perfectly symmetric. The object hits the ground with the exact same speed and angle that it started with, confirming energy is conserved. A fascinating fact is that two complementary angles, theta and 90 minus theta, result in the same horizontal range, for example, 30 degrees and 60 degrees. We can link the horizontal distance and the vertical height directly. The range times the tangent of theta always equals 4 times the height. Since g is in the denominator of all our formulas, a smaller gravity means the object will stay in the air longer, fly higher, and travel much further. On Earth, air resistance changes the path. Drag force makes the landing steeper and shortens the range, turning the symmetric parabola into a slightly squashed curve. This table summarizes all our hard work. These 4 formulas are the backbone of projectile physics, allowing you to predict flight by knowing initial speed and angle. A key thought experiment proves that horizontal motion has 0 effect on vertical fall speed. If you drop a ball and shoot a bullet horizontally at the same time, they hit the ground at the same second. From an energy perspective, the object trades speed for height, converting kinetic energy into potential energy on the way up, and reversing perfectly on the way down. At every point in the path, the acceleration vector points straight down. This constant vertical pull is what creates the curved parabolic path. When the object finally hits the ground, its horizontal speed is the same. Its vertical speed has the same magnitude but is pointing down, confirming the symmetry theory. Remember that our simple formulas assume the object lands at the same height it started. If the target is at a different height, you must use the basic kinematic equations. If you fire an object horizontally, the angle theta is 0. In this special case, the object only describes half a parabola with constant sideways motion and downward fall. We can verify our math using dimensional analysis. Checking the units proves that our range derivation is logically consistent, resulting in a length unit. In conclusion, we have rigorously derived the laws governing projectile flight. You now have the tools to analyze any object moving through a gravitational field.